In this video, I will be talking about second order differential equations, specifically solution types for second order differential equation. How do we find a solution for a specific second order differential equation given to us? It is very important that we know the types of solutions we must get for a second order differential equation before we tackle any question under such topic, because it is very tricky, a little bit cumbersome, and so you need time to go through all the solution types for the complementary function, the particular integral function, to be able to generate the general solution for a second order differential equation. In this video, I have a function of this form. Any function of the form a d square y dx square plus b dy dx plus cy equal to f of x. It's a second order differential equation where a, b, and c are constant. These are numbers that can be positive or negative. Now, the f of x here is another function on its own in terms of the variable x, depending on the question given. And this f of x is used to generate the second part of the solution called the particular integral solution. Then the derivative part of this side, a d square y plus b dy dx plus cy, will be used to generate the complementary function. So the general solution for this second order differential equation will be y equals complementary function plus particular integral function. However, before we can solve for the complementary function, we need to assume that f of x is equal to 0. This is a proof. I don't need to prove it because it's very cumbersome, so I will just explain it in short, simple statement. When we assume that f of x is equal to 0, we can work for the complementary function such that the whole function on the left side equal to what? 0. Now, to be able to work on this, we need to change this to what we call the auxiliary equation. And usually, we use m, the letter m, to represent the derivative terms to change the function into a quadratic equation. And once we are able to get that quadratic equation, we solve for the roots of m, or for the root of that equation, to generate the answers that we need. These will help us to be able to find the solution for the complementary function. And so the quadratic equation that we will generate using the letter m to represent the derivative terms, we call it the auxiliary equation. To generate the auxiliary equation, we just represent the derivative term d square y dx square and dy dx with the letter m. Now, this is second derivative, so we square it. M square will be equal to d square y all over dx squared. And then dy dx will be equal to m. So that when I substitute m back into the equation, I will get a m square plus bm plus c. Forgetting y, don't work with y, equal to 0. Now, we have generated what we call the auxiliary equation, am squared plus bm plus c equal to 0. Now, this auxiliary equation is a quadratic equation. When we solve it, we generate the root of m for m1 and then m2. And these roots will be used to determine the solution type of the second order differential equation, only for the complementary function. For f of x, which is the particular integral, I will talk about that when I am working on an example in my next video. Now, the first solution type I'll talk about is when the quadratic equation, which is the auxiliary equation, generates real and different roots. This means that the values or the root of m, or the root of the quadratic equation you will get, will generate a root that are real, and by the end of the day, they are of different values. So I will take an example. When we look at this example, we see that the function is giving us the square y all over the x squared plus 5 dy dx plus 6y equal to 0. The coefficients of the second derivative term here is 1. Now, let's generate the ODE equation to find the complementary function. So all you need to do is that you represent these ones by the variable m. So the ODE equation is m squared plus 5m plus 6 equals 0. So we have m squared. You can just punch this on your calculator to generate the root of m, and then you use it to solve. M squared plus 2m plus 3m plus 6 equals 0. When I add this and this, I will generate that. So I can factorize this by saying m outside, m plus 2 plus 3 outside, m plus 2. So that this time this will give me 3m, this time this will give me 6 equals 0. So I pick m plus 3 and then m plus 2, one of them. So m plus 2, m plus 3 equals 0. So this means that m plus 2 equals 0. Therefore, m1 equals minus 2. And then m plus 3 equals 0. Therefore, m2 equals minus 3. Now, when we look at this, these two values are the root of what? The auxiliary equation. They are two different values, but however, they are real. So that means we have real and different what? Root. One is negative 2, one is what? Negative 3. Or one is 2, one is 3. Now, if the roots are real but of different root, how do we generate the general solution? Then the general solution becomes y equals a e m1x plus b e m2x. So a exponential function m1x plus b exponential function. So when I substitute the values of m1 and m2, this is what I am getting, and this is my final result. Note that a and b are arbitrary constants, and m1 and m2 minus 2 minus 3 are m1 and m2 from the auxiliary equation we created, and this will be the solution for a second order differential equation having two real roots, but these real roots are different. Maybe you may be asking, why did I write the solution using arbitrary constant? In the beginning, I told you that for me to prove to you that the solution will be in terms of a exponential function, this and that, is very cumbersome. So I will not be able to talk about it. So if you really need further information about this, you need to read under second order differential equation. It is a proof. You take it like that. If the root of the function or of the quadratic function are 2, such that these real roots are different but they are real, then it means you write the solution a, b, e the first one, and then e the second value. Let's consider another example. We have d square y dx squared minus 7 dy dx plus 12y equal to 0. I have already deduced the complementary function. That is why I equate the function to 0. Now, first we find the ODE equation. And to find the ODE equation, say that ODE equation is m squared minus 7m plus 12 equal to 0. So now that we generate that, we have to divide it, we have to factorize this. Use your calculator to do that, and this will give you m squared minus 3m minus 4m plus 12 equal to 0. I can factorize this by saying m outside, m minus 3 minus 4 outside, m minus 3 equals 0. So we pick one of this and we pick m minus 4. And we have m minus 4, m minus 3 equals 0. And so the solution for the complementary function becomes y equals a e 3m plus b e 4. This is supposed to be x, not m. Sorry for that. So we have y equals ae 3x plus be 4x, and this is our solution for your complementary function. You then find the solution for the particular integral function. You add it to this one to generate your general solution, but that is not what we are doing. Let's talk about the next solution type. Okay, so what if the roots are rather real and equal? This is what we call the second solution type. Now, this time, the roots of the ODE equation will be real, but they will be of the same value, and this is how we generate it. So let's find the ODE equation for this example we have here. For this one, we have m squared plus 6m plus 9 equals 0. So we have m squared plus 3m plus another 3m plus 9 equals 0. This plus this will give you 6m. So we have, I will factorize m squared plus 3m. So m outside, m plus 3 plus this and 9. 3 outside, m plus 3 equals 0. So that this and this will be my solution. So m plus 3, then you pick any of the ones in the bracket, m plus 3 equals 0. So m plus 3 equals 0. Therefore, m1 equals negative 3. And then m plus 3 equals 0. Therefore, m2 equals minus 3. Now, when you look at this root very carefully, you see that they are the same. That is equal roots, but they are also real. So that is what we are talking about. What will be the general solution for y in terms of this function? So this one, we have y equals e raised to the power minus 3x into a plus bx. So, for you not to be confused for what I have done, I'm going to explain it. Now, in normal circumstance, you were supposed to get y equals a e minus 3x plus b e minus 3x. This was what we did for the first one, but you should know that every second order differential equation will have two arbitrary constants, which is a and what? B. So there must be another term containing what? A constant. Remember, there must be another term on this side containing a constant using the variable x to represent it. So whatever we did, the solution was supposed to be y equals a minus 3x plus bx e minus 3x. And this is the other term we are talking about. And this must have an x, so that when you work the solution with a particular integral, you will not get it wrong. Especially if you are finding the values for a and what? B. So now you can see that this and this, they are common. So I can factorize it out by getting y equals e minus 3x into a plus bx. And this is what I have here. So this is my final solution. So you generate this type of solution when the roots are real but the same. So this is what you will get. Now let's take the last example. In our second example, we have d square y dx square plus 10 dy dx plus 25y equals 0. To generate the auxiliary equation, we just say that m square plus 10 plus 25 equals 0. This is very simple. So we have m square plus 5m plus 5m plus 25 equals 0. 5m plus this will give us 10m. So m outside, m plus 5 plus 5 outside, m plus 5 equals 0. So when you work on this, you get m plus 5 equals 0. Therefore, m equals minus 5, m1, and then m plus 5 equals 0. That is m2 equals minus what? 5. So the final solution will be this and this are the same, they are real and the same. So we have the general solution for the complementary function is y equals e raised to the power 1 of this minus 5x into a plus bx. And this is your solution for the complementary function. So let's talk about the next solution type. Now, this is complex root. What if the roots of the quadratic equation are complex? This is where most students find it very, very difficult. I remember I used to find it very difficult. Now, pay attention critically to whatever I am coming to do, because you need to understand this. Now, when the roots are complex for the auxiliary equation, then we will generate something like the m will be equal to a plus ib, where a and b are the constants, either positive or negative values, and I representing the imaginary what form. This means that our m1 will give us a plus ib, and our m2 will give us a minus what ib, if you generate the complex roots. Now, then your general solution will be in the form y equals, let me use c and d as the arbitrary constants. I know why, I will explain. So it will be in the form c e m1 x plus d e m2 x. Now watch carefully. What is m1? m1 is this. So we have y being equal to c e a plus ib x plus d e a minus ib x. This is what we have. Now, the next thing you should know is that I can use indices to expand this thing, because if I have a plus b, let's assume I have a plus b all raised to the power this, I can change it to e raised to the power e plus times, rather e raised to the power e times e raised to the power what? ib. So now let's rewrite this form. We will have y equals c e raised to the power e x. Don't forget the x is multiplying everything. X multiplies e, x multiplies ib, times e raised to the power ib x. This is what this side means. Plus d e raised to the power a x times e raised to the power minus ib x. Now this is what you are going to get. Now, in complex notation, it is something you must put in your mind. In complex notation, I don't want to talk much about it, so I'll just state it. In complex notation, the exponential function to power ix, this one, ix, forget about the arbitrary constant b, ix is the same as cos x plus I sine x. So I'm saying that ix is the same as cos x plus I sine x, and the negative, which is this one, negative ix, will be e negative ix equals cos x minus I sine x. Now, if we have this knowledge, then we can substitute these two things here. But let's not forget that there was a b here and there was another b here. So I can add the b's to it. So let me rewrite this in the form. So in general term, it is supposed to be what? Let me separate this one. It is supposed to be EIBX. So therefore, then we will get cos BX plus I sine BX. And then this one to give us e raised to the power minus IBX will be equal to cos BX minus I sine BX. This is what we have. Now I am coming to substitute everything I have here to replace this one and this one. And then let's see what we are going to get. Now note that a raised to the power, the exponential function e raised to the power ax and e raised to the power ax here, they are the same. So we can factorize it out. So I can say that generally y will be equal to e raised to the power what? Ax, and I'll bring my bigger bracket. Now when you look at this, I have factorized this one out, so I'm left with this. This side is equal to, this is what we have here. So, but it is multiplying the arbitrary constant c. So I'll bring my c, then into bracket cos bx plus I sine bx. Then I can close my bracket plus I have d here. I've already factorized this one, which is here. So I'll put my d, then into bracket I will substitute I minus bx, which is cos, which is this one. So when we put it there, we get cos bx minus I sine bx, and close the bracket. Then there's one big bracket I need to close. The paper is not big enough. Now, what is the next thing you can do? All you need to do is that use c and d to multiply through. So I have y equals e raised to the power ax into bracket. Then when I multiply this, I'll get c cos bx plus c I sine bx plus d cos bx minus d I sine bx. Now you can group all cos to one side. This is cos, this is cos. So I will get y equals e raised to the power ax, bigger bracket. Then I'll have c cos bx plus d cos bx. This and this are the same, so I'm grouping like terms. Then plus, I'll take this one, c I sine bx, and I'll take this one minus d I sine bx, and I'll close my big bracket. Now, we can factorize C and D out because C and D are what? They are the same. So when I want to do this, I'll just say that y will be equal to e raised to the power ax into C plus D, all multiplying cos bx. So that when I multiply this, I'll get this. When I multiply this, I'll get this. Then plus, there's an I here, there's another I here. I can factorize that one out. So I'll see I outside, C minus D. Then I'll pick one of this, sine bx. And this is it. Now, look at this very carefully. I'll factorize C and D, and then C and D here, sine bs, I is here. Now, let's now say that let the arbitrary constant A be equal to C plus D, and let B be equal to C minus what? D. What are we going to get? We are going to get y equals e raised to the power ax into bracket a cos bx, then plus what? Let me explain this one again. Let's represent b by I C minus D. Do we get it now? So that I can just use b here. So plus b, then I repeat this, sine bx, and this will be my final answer. Now, whatever we have generated here is the general solution for the complementary function. Whenever you get a complex root, where this complex root has the real value and then the imaginary term. Note, the root is complex, however, it has a real value and an imaginary term, and your general solution will be of the form this: a raised to the power as, e raised to the power ax, where a is your real value, and then b becomes your imaginary value. There is no need for you to bring an I to represent it. You just pick the b and the b and you substitute there. Secondly, the interesting thing about this is that you don't need to pass through all these steps to generate your answer. All you need to do is keep this in your mind. Keep this in your mind. Once you have this in your mind, you can generate everything. And so this means that your y general will be a cos bs plus b sin bs, and you bring e outside to your real number, which is ax, where a is any number that you get for m here, and b is any number that you get for b here from the quadratic equation. So I will now take an example and then we use it to generate the answer. So the only interesting part of this is that keep this in mind. That is all. I just have to prove this one for you to understand why we are generating this, but it is not important. Just keep this in mind. So let's take this example. Looking at this, what will be our ODE equation? The ODE equation becomes m squared minus 2m plus 10 equals 0. For you to be able to be sure if you can factorize this one so easily, you need to test it with a calculator, because in Probably if you are solving this in exams, you do not have time to be thinking about how to factorize this. So you just use your calculator to check if it will be what complex. Now this is my calculator, and the coefficients of m square is what? 1. So I input it, I press equal to, the next one is minus 2, I press equal to, the next one is what? 10, the constant is 10, I input it. Now when I press equal to, this is my solution. The first one is 1 minus I3 or 1 minus 3I. This means it's complex. The next one is what? 1 plus what? 3I. This is also complex. So it's telling us that this is not an ordinary function. It's a complex what? Function. That means the roots are complex. So we use the quadratic equation to solve it, because you need to show work if you are producing this in exams. So to solve this, you just use the quadratic equation to do it. The quadratic equation is minus b plus or minus root of b squared minus 4ac all over 2a. So I'll input the values. This is a, the coefficient here is a, this is b, and this is c. So when we put it inside, we are getting, there is already a minus here, and b is also minus 2, so I'll put it into brackets. Then plus or minus root of minus 2 all squared minus 4. What is a? A is 1. And what is c? C is 10. So this is what I have, all divided by 2 into what? 1, where a is 1. This time this will give me what? 2 plus or minus root of, this will give me 4 minus 4 times 10 times 1 will give me minus what? 40. This is it, all over 2, 1, 2. So when you continue solving this, you will get 2 plus or minus root of minus 36 all over 2. Now, to work on this one, you need to take the root of this times, so this becomes 2 plus or minus root of 36 times root of minus 1. When you multiply this, you get this, because we want to get rid of what? The negative. This time, this will give you the same thing. So now, all about 2, but root of minus 1 is equal to what? I, where I is the complex notation. So now, I'll substitute I here to get 2 plus or minus root of 36i all over 2. And root of 36 will give you 6. So you are getting 2 plus or minus 6i all over what? 2. You can rewrite this by saying this is 2 over 2 plus or minus 6i over 2. This will take care of this to get 1, 1. This will go here, this will go into this 3. So you are getting 1 plus or minus 3i. So therefore, in the question, your m1 is equal to the positive side 1 plus 3i, and m2 equals 1 minus what? 3i. So this is what we have generated. Now watch carefully. This is not the time for you to be learning how to use how to use the quadratic equation. You should know this. Whatever level that you are, you should know this. So now this is what I've gotten. Now I can see that the roots are complex, and it has a real value and an imaginary what? Side, the complex side. So everything here is what? Complex. So what will be our general solution? We have already discussed how to generate the general what? Solution. So this is it. This is what we will write as our general solution. So we substitute A here, and note that this is A, this is A, and this is what? B. So our general solution becomes y equals e raised to the power ax, where a is 1. So it is 1x, the same as x. Then into brackets we have a cos bx, and what is b? B is 3, so a cos 3x plus b sine 3x. You will be asking me, why is it that the I did not appear here? This b, or this formula, has already taken care of what? The I. When you look at this one, you see that we represented b with I, c minus what? D. So there's no need for you to bring an I here. The I has already been taken care of by b, and this will be your solution for the complementary function. So this is a solution. This is how you produce your solution for the complementary function, no matter what you get here. If it is in the complex form, where you have a real and imaginary form, this is how you generate your final answer. All you need to do is to keep this formula in mind and use it to generate your answer. I hope this has been helpful. Now let's move on to the next one. Case 1. What if we have a function of this form? The square y over the x squared plus n square y equal to 0. I'll take an example so you understand. Let's derive the auxiliary equation. The auxiliary equation becomes m squared plus, there's already an n here, so there's no need for us to repeat m, plus n squared equals 0. So now I want m, so m squared, I'll carry this to this side, will be equal to minus n squared. If I want to make m the subject, I'll take square root of both sides. So root of m squared equals root of minus n squared. This will take care of what? This one. So this is giving me m equal to root of what? N squared times root of minus 1. So when I multiply this, I generate this. Now this will take care of this. So m equals n times, this is I, root of minus 1 is I, times I, the complex I. So m equals, let me see, I n. Now when you look at this, this has given us the root of what? M. And n is what? Complex, but it has no what? Real part. In normal circumstance, m is supposed to be, this is plus or minus what? I n, because we have taken the root of that. In normal circumstance, m is supposed to be a plus or minus ib. We are already aware of that. But however, a equals 0 and b equals n. So n here equals b, and then a equals what? 0. So this one, we are seeing that though we generated a complex root, the a was 0. That is, the real part was equal to what? 0, and the imaginary part, which is n, was given. And this value is the same, but there are two of them. One is positive and one is what? Negative. So now let's move on to the example, the previous example we spoke of. The previous example, we said that if it is complex, then we have EAX, A cos BX plus B sine. This time we are representing B with what? N. We they are representing b with n. So now the general solution will be this. Now if the general solution will be this, then we have a will be equal to e raised to the power 0x, because our a was 0, and this will give us a cos nx plus b sin nx. This will be our general solution. Anything to power 0 is 1. So we are going to get y equals a cos nx plus b sin nx. This is the solution for any differential equation, second order differential equation, having complex what? Roots, where the real term equal to 0. So you are going to say that therefore y equals a cos nx plus b sin nx. And this is the solution for case 1. Case 1, where n is complex and a is 0. So let's take one example for this one. In our first example, we have the square y dx squared plus 16y equals 0. This is the function given to us as the complementary function. So now let's solve this. Auxiliary equation becomes m squared plus 16 equals 0. So therefore m squared equals minus 16 m squared, that is root of m squared, equals root of minus 16, and so this will cancel this. M equals root of 16 times root of minus 1. M equals plus or minus 4, and this one is what? I. Don't forget, root of negative 1 is the I, and it is multiplying the root of 16. So m1 equals 4i, m2 equals what? Negative 4i. Now, these values are complex, and they are not the same. However, now these values are complex, and they have their real term to be what? 0. So the general solution will become y equals a cos 4x plus b sin 4x. Don't worry about the negatives, because this sign has already taken care of that during the proving. So this is your what? M1, M2, they are the same, and so you just put it here, and this is your final solution. As we proved, I've already proved this, so there's no need to worry about it. So this will be your general what? Solution for the complementary what? Function. Now, in case 2, the value here will be negative, so when you take it here, you produce a positive value, so that when you take the root, you get a real number giving you the root of what? M. So the auxiliary equation becomes m squared minus n squared equals 0. So it is m squared, when I carry this side, equal to n squared. So root of m squared equals root of n squared. This will take care of this, giving me m equals plus or minus n, so that this one will take care of this. Now, watch carefully. The root of m is giving us an answer in real term. This one, it is a real value. It is not complex, and this real value is 1 positive, 1 negative. The same value, but one is positive, one is negative. Let's forget about the positive and negative and focus here. This time, it is not complex, but it is what? It is real. What will be our general solution? Note that in the beginning, when we were working for real and different roots, we realized that when it is real and differential, we generate y is equal to a, e, this, b, the. It is the same process, but this time we will write the answer in hyperbolic functions. So now this, our general solution for y will be y equals, let me use c and d as the constant because I'm dealing with what? The complex root. So c, e raised to the power what? The first positive number nx plus d, e raised to the power the negative number minus nx. You all understand? So that if I have a value for n, one will be positive, one will be negative. The positive side first, then the negative side. But this is not how you write your final answer. You need to change this to what we call a hyperbolic function. And to take this into the hyperbolic function, your general solution for y will be y equals a cos nx plus b sin nx. This is what you write for him as your final answer. After you have generated this, you change it to what? The hyperbolic function. You will not be asked to prove why you got cos and sin. You will not be asked to prove it. But for a student to understand this, I am going to prove it. There is no need. All you need to do when you get here, change it to this form. But I am going to prove it so that you understand the reason why e raised to the power ns is what? Cos ns, and e raised to the power minus ns is what? Sin what? Nx. So now let's prove this. In hyperbolic function, I'll work with cos and sin. Cos and sin are hyperbolic functions. So in the hyperbolic function, you should note that cos nx is the same as e raised to the power nx plus e raised to the power minus nx all over what? All over 2. This is a general rule for this one. Then sin nx equal to e raised to the power nx minus e raised to the power minus nx all over what? 2. Let's add cos and sin and see the result that we get. Adding both, we have cos nx plus sin nx, and this will give us this plus this. We have e raised to the power nx plus e raised to the power minus nx all over 2 is equal to cos. Then we add it to the sin, this side. We have e raised to the power nx, e raised to the power minus nx all over 2. Now, when I get here, I can take LCM. So what will be my LCM? My LCM is 2. I'll take 2 as my LCM, the lowest common multiples. 2 will go into this one, 1. 1 times the numerator will give me the same thing, e raised to the power nx plus e raised to the power minus nx plus this plus 2 will go here, 1 times everything here will give me e raised to the power nx minus e raised to the power minus what? Nx. Now when you get here, look at this very carefully. This side and this side are the same. They can cancel. This is negative, this is positive. So this will cancel what? This one. Now we have cos nx plus sin nx being equal to e raised to the power nx plus e raised to the power nx all over what? 2. This plus this is the same. So I can add them together. But before I do that, let me factorize this. Whatever I have here is the same as 1 over 2 into e raised to the power nx plus e raised to the power what? Nx. We all understand. So that when I multiply 1 by this, I'll get this. 2 by the division 1, I'll also get the same function. This plus this will give me 2e raised to the power nx. So this is giving us 1/2 multiplying 2e raised to the power what? Nx. And so therefore, these 2 will now cancel this one, giving us what? E raised to the power nx. So therefore, cos nx plus sin nx equals e raised to the power nx. The addition of cos and sin will give you e raised to the power ns, and it is what is representing this side. So e raised to the power ns is equal to what? The sum of cos and what? Sin nx. Now let's subtract both and see the result that we will get. Will give us what? What is cos ns? Cos ns is this, and this is sin nx. So we are getting e raised to the power nx plus e raised to the power minus nx all over 2 minus e raised to the power nx minus e raised to the power minus nx all over what? 2. So the LCM here will be what? 2. 2 into this 1 times the numerator will give us e raised to the power nx plus e raised to the power minus nx. Then this minus sign will come. I'll bring a bracket. So now this into this will give me what? 1 times the numerator will give me the same thing. E raised to the power nx minus e raised to the power minus what? Nx. Bracket close, so that this can affect everything in the bracket. Now this is going to give us e raised to the power nx plus e raised to the power minus nx. This time this minus e raised to the power nx. This time this will give us plus e raised to the power minus nx all over what? 2. Now when you watch carefully, this and this are the same. This is negative, this is positive. So this will now take care of this, and we will be left with this one. So this is going to give us e raised to the power minus nx plus e raised to the power minus nx all over 2. So therefore, cos nx minus sin nx will be equal to 1/2 e raised to the power minus nx plus e raised to the power minus nx. So this is the same as 1/2 2e raised to the power minus what? Nx, because this and this are the same. This will take care of this, and this will give you e raised to the power minus what? Nx. So therefore, cos nx minus sin nx equals e raised to the power minus what? Nx. Now, after we combined and subtracted both equations, we realize that cos ns plus this sin ns will give us this, and then when we subtract, we get this. Now, in the general solution for this one, we said that y is equal to c e ns plus what? D minus ns. So let's put it down. We have y equals c e nx plus d e minus what? Nx. Now we can substitute, because we know this to be this and we know this one to be this. So now let's substitute. This is the same as this, which is equal to this. So I'm substituting this and this into the formula, and I'm getting y equals c outside. Watch carefully. E raised to the power ns is the same as this. So I have cos nx plus sin nx, bracket close, plus d into bracket. This side is the same as this, so I'm substituting this with this. Cos nx minus sin nx, bracket what? Close. Now we can use c to multiply through and d to multiply through, and this is giving us y equals c cos nx plus c sin nx plus d cos nx minus d sin nx. So now group like terms, group all cos and all sin. So therefore y equals c cos nx plus d cos nx plus c sin nx. This one. Then I'll bring this one minus d sin what? Nx. So now I can factorize one of this c and d by saying y equals c plus d bracket cos nx, so that this time this will give me this time this will give me this, then plus c minus d multiplying sin nx. Now we are almost there. Then when we get here, we will say that but let a be equal to c plus what? D, and let b be equal to c minus what? D. So therefore y is going to give us a cos nx plus d sin nx. This is the proof. So I have proved to you the reason why the general equation, when the root of the auxiliary equation is what? Is real, and the complex factor or the complex side is what? 0. This is the general solution. So taking you back, when I tell you that y is equal to c raised to the power ns plus d raised to the power minus ns is equal to this, do not be what? Confused. This is the proof. So all you need to do is that put this in your head for special case questions. So put this in your what? In your head for special case question, and you'll be good to go. So I'll take one example under case 2, and then we are done for this video. Now, when we look at this example, the auxiliary equation becomes m squared minus 3y equals 0. So therefore, there is not supposed to be a y here. M squared minus 3 equals 0. So m squared minus 3, let me rewrite, equals 0. M squared equals 3. So this is giving us root of m squared equals root of what? 3. So this is giving us m equals plus or minus root 3. There's no need for you to change the value, just leave it like this. Now when we look at this, this has generated the solution for what? N, where root 3 equals what? N. So therefore, what will be the general solution? Y will be equal to c e raised to the power what? Root 3 x plus d e raised to the power minus root 3 x. But you don't leave your answer like this. You change this into hyperbolic function by saying therefore y equals a cos root 3x plus b sin root 3x. Remember that this formula has already taken care of the negative here. So this is your final answer. For complex functions, there are 2 special cases. In my next video, I'll be taking examples under second order differential equation for both the complementary function and then the particular integral solution. So that one, you will see a clear example of what we have spoken of here. Thank you very much for joining me here in this video. My name is Daniel, and I'll meet you in my next video. Stay tuned. Subscribe to this channel if you have not.